Hello everyone, let us not waste much time and start our preparation for class 10th as per the syllabus. In this module, you'll be getting mathematics as per NCERT syllabus, and if somebody have any doubt, please comment below. So the first chapter is real numbers. What is real numbers actually? So the real number is a set of natural numbers, whole numbers, integers, rational numbers. We all know what is natural numbers, and we all know about whole number, integer and rational number. And apart from the real numbers, we have imaginary numbers, which includes a number which cannot be represented on the number line. So a real number we can state as a number which can be represented on a number line. So imaginary numbers are like minus of root of any number. Okay, this is imaginary number because it is not possible to get a negative number under the root, square root. And other real numbers are irrational numbers, rational numbers. All these numbers are real numbers. Okay, so the first topic of this chapter at page number 2 and 3 is theorem 1.1, that is Euclids division lemma or Euclids division algorithm. First of all, lemma. What is lemma? Lemma is a proven statement that is used to prove another statement, and similarly the algorithm is the steps we are taking to solve any problem. These are called algorithm. So what Euclid said, that when we divide a number, we call it a dividend. We divide it with the divisor and the answer is quotient, and we have a remainder. So in this way, dividend is equal to divisor into quotient plus remainder. Okay, let's say this dividend is A and the divisor is B, quotient is Q and remainder is R. So Euclid termed it as this as division, Euclid's division lemma. Okay, so in this part we have a very important thing, that is the R should be less than B and greater than or equal to 0. So let us take an example, like we need to divide 11 with 2. So what we'll do, we'll divide it like this, right? So let's say this is A, this will be B, this will be Q, and this will be R, right? So we can write it as A equal to BQ plus R, that is 11 equal to 2 into 5 plus 1. So is it satisfying this equation as well as this lemma? And we can see that this R is in between B and 0. R can never be greater than B and R can never be less than 0. Okay, now we can use this Euclid's division lemma to find the HCF of any two given numbers. Like to find the HCF of 420 and 130, we can write that 420 is equal to 130 into 3 plus 30, right? Obviously we will divide 420 with 130. So you can do the division in rough if it is required, and then the next step will be 130, that is equal to this 130, this B will become now A, and this R will become now B. Okay, then similarly in this step also this B will become A and this R will become B. This is the important transition here. And the step where we get 0 as our remainder, the B of that step will be the HCF of these two numbers. Okay, the B of that step where we get remainder as 0 will be the HCF of these two numbers. Okay, so HCF of 420 and 130 is how much? That is 10, right? I'll be explaining the presentation part of this question in the exercise itself. So the next topic is theorem 1.2, fundamental theorem of arithmetic. It is nothing but the prime factorization. Like when we say 120, any number like 120 can be written in its prime factor form, the factors form, that, and those factors will be prime numbers. Okay, so prime factorization, like we can write this as like 3 2 2 2 8, 5. So irrespective of the order of the prime numbers, we can write any numbers in its prime factor form. That is a basic theorem, we all know it. So now let us start the exercise 1.1, question number 1, in which we need to use Euclids division algorithm to find the HCF of the given two numbers. So the question is 196 and 38220. So obviously 38220 is larger number, so that will be A, and 196 will be B. We need to find Q and R. Okay. So you can see the 196 into 195, that is 38220, and we have got remainder 0. So HCF will be what? The B is the HCF, right? As I've told you earlier, that B is the HCF. So 196 is the HCF of 196 and 38220. So now I'll explain the third part, and I'll explain how you have to answer it when it is asked in the examination. The presentation is important. Always remember that presentation is very important, because it will bring more marks with a good presentation. Many times you know all the questions, but you'll not get full marks if your presentation is wrong, if your presentation is not correct way. Okay, so presentation is important. So in this question I will teach you how to write it during your exams. Okay, so as we know, this is the first number. So this is the greater number. So this is A, and this will become B. You have to write the whole theorem, the Euclids division lemma, like this. Okay. So this will become A, and as per this A equal to BQ plus R, we will put this. We can divide it here. You can show the division, or you cannot. You can skip the division. That is not important. But the Euclids division lemma, step by step, that is always important. Okay. So as I have already explained, that this B will become the A for the next step. See, I'm making these arrows. You don't have to make these arrows, obviously. So this is the proper way of doing this question. You have to write here, since R is not equal to 0. Since R is not equal to 0. This part is not that important, but of course it looks good that the child understands why we are going on and on. We have to do this until we get R is equal to 0, and when the R is 0, the B will become the HCF. Okay, so this B will become A, and this R will become the next B. This B will become A, and this R will become next B. So this R is 0, therefore the HCF is this B. Okay, I hope you understood the concept as well as the presentation style. So let me give you some homework. For note down the homework and comment the answers when you're done. Now let's go to the second question of the first exercise. Here we need to show any positive odd integer in the form of 6q plus 1, or 6q plus 3, or 6q plus 5, where q is some integer. So according to Euclids division lemma, let A be any positive integer, not the odd integer. A be any positive integer and B be 6. Okay, so by Euclids algorithm, we can write as A equal to BQ plus R, where A is equal to 6Q plus R. Now R can be either 0 or less than 6. So we have 6 values of R, that is R can be 0 or 1 or 2 or 3 or 4 or 5. R cannot be 6 or less than 0. And also we have to mention here that Q is some integer not equal to 0. Okay, so now these are the 6 possibilities of A. A can be 6q plus 0, A can be 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. These are the 6 possibilities to write an integer A with B equal to 6. So we know that 6 into anything, 6 is an even number. So 6 into any integer will be what? Will be an even number. So this is even, right? This is even, because even plus even is even. So to get odd number out of an even number, that is only possible when even number is added to odd number. So this is an even number and this is odd, so even plus odd is odd. Similarly, even plus odd. Now we are asked that what are the odd numbers in this present scenario. So in this present scenario, if A is an odd number, is an odd positive number, any positive can be written as 6q plus 1, 6q plus 3, 6q plus 5. So this is the required answer. You don't have to mention this part here. Okay, you just have to write that A can be written as in this form, in 6 of this form, and we need positive odd number, therefore these are the possible positive odd numbers. Okay, so that is odd, this odd, and this odd. These 3 will be written here. You don't have to mention this part. Okay, so in the next question, question number 3, we have an army contingent of 616 members, and they will march behind an army band of 32 members, and we need to find the maximum number of columns. So we simply need to find the HCF of 616 and 32, and this will give the maximum number of columns. Okay, so according to Euclids division lemma, A equal to BQ plus R is in between 0 to B. 616 is greater than 32, so it will become A and this will become B. And in this way, we can conclude that HCF of this number is 8. So always remember this concluding statement, that is, they can march in 8 columns. So the next question is similar to the second question. In this, we need to use the Euclids division lemma to prove that square of any positive integer can be written in the form of 3m or 3m plus 1. So as per Euclids division lemma, A equal to BQ plus R, B we have taken 3. So A will be equal to 3Q plus R. So R can be of 3 values, that is 0, 1 and 2. And for that, we will have 3 possibilities of A that we'll write here. So we have these 3 possibilities, that A is equal to 3Q or 3Q plus 1 or 3Q plus 2. And we will have to prove for each and every one of them that we can write the square of A as 3m or 3m plus 1. So the first case will be, we will square this first case, and we will take 3 common, and we will take 3q as m. So this will become 3m. Okay. So for the next one, we will square this one. A square will be this one, and we have applied which identity? The A plus B whole square, that is A square plus B square plus 2AB, right? And we will get 9q square, 6q square, and we know that 3 is common here, so we'll take the 3 common, and this time we will take this term as m. Okay, m is some integer, right? So this is an integer because we have taken q as an integer as per the Euclids division lemma. So this will become 3m plus 1. This 1 will remain alone. So this for the third term, 3q plus 2 whole square we will take, that is A square plus B square plus 2AB, and we will get this term. Now for this one, we don't have anything common in 4, so we will split this 4 into 3 plus 1. 3 plus 1, that is 4. So now we have 3 common in this term. Then we will take out the 3 and we'll have this. Now this term will be m for this case. Okay, so this is 3m plus 1, 3m plus 1, 3m plus 1 and 3m. We have accomplished what we were asked to do. And now the last question of the exercise, that is the same question as in question number 4. Now we have to prove the cube of any positive number in the form of 9m, 9m plus 1 and 9m plus 8. Okay, or 9m plus 8. Okay, now here also we can take b equal to 3, b equal to 9, like we have taken b equal to 3 for the last question, because we need to prove 3m plus 1 and 3m. Now we need to prove 9m plus 1 and 9m plus 8. So why don't we take 9, b equal to 9? Yes, we can take b equal to 9, but the problem is, if we take b equal to 9, then we have to prove for 9 situations, like r equal to 0, r equal to 1, 2, 3, 4, 5, 6, 7, 8. We have 9 situations. We have to prove all of them individually. That will be too long, and plus it is not required, right? Maths is all about doing the right thing and not the unnecessary things. Okay, so we will not do that. We will take b is equal to 3. So I'm not going to write the statement part again, because it's the same thing, same like question number 4. I'll just do the question. So we are having 3 situations, that is r equal to 0, 1 and 2. So like the last question, we have 3 situations and we will have to prove for each of them. So like this, I have cubed both sides and 9 is common, and I have taken this term as m, just like the last question. Okay, now we will have to cube this part also. So what is the a plus b whole cube? Can anyone tell me? Can anyone recall what is a plus b whole cube? Can all of you recall what is a plus b whole cube? A cube plus b cube plus 3a square b plus 3b square a. B is 1. So we can see that there is 9 common in every term except this one. So we'll take out the 9. So we have taken out 9 and 1 is remaining. So we'll take this part as m. So now this is m plus 1, right? So for the next part we will cube this term. Now this we will take as m, and we have 3m plus 8. So these three were the terms we needed to achieve, and we have achieved that. So that's all for today's class. I'll give you some homeworks related to this question. Let's meet in the next class. Stay safe, stay at your homes, and keep studying. Okay.